Section: Introduction. In this section, we discuss the necessity of pixel-level loss in image autoencoders to measure and reduce distortion. A common choice for this is mean squared error, or MSE. However, MSE tends to favor low-frequency details over high-frequency ones, which can be problematic for image and video models. While there are robust loss functions available, they alone do not prevent blurry reconstructions. A typical solution is to combine pixel-level loss with additional penalties, often still using MSE due to its straightforward optimization. For instance, we might combine MSE with perceptual loss and adversarial loss, where adversarial loss helps produce high-quality images with realistic textures. Yet, training generative adversarial networks, GANs, can be difficult, as noted when attempts to scale their architecture face challenges. Additionally, modern GAN decoders are deterministic, limiting the diversity of their outputs. As an alternative, we propose a method that utilizes diffusion loss for learning an autoencoder. This diffusion loss is advantageous because it is a proper scoring rule with beneficial theoretical properties, including a formal connection to KL divergence. It has shown the ability to generate clear results with high perceptual quality, as confirmed by human evaluations. To illustrate its simplicity, we integrate a popular encoder architecture with a U-net decoder, which is well suited for denoising and diffusion processes. We provide further details in the methods section, demonstrating that our approach achieves lower distortion across all compression levels, as measured by the CMMD metric. Our decoder can sample details at test time that are not captured in the latent representation, leading us to name our approach, Sample What You Can't Compress, or SWYCC for short. We will show that SWYCC results in lower reconstruction distortion at all tested compression levels compared to state-of-the-art GAN-based autoencoders. Additionally, SWYCC representations yield qualitatively better latent diffusion generation results across all tested compression levels. We also find that splitting the decoder into two parts enhances training dynamics. In terms of methodology, we briefly outline the standard diffusion loss, which is characterized by a Monte Carlo approximation. Here, we denote a natural image as X, and D represents a neural network trained using gradient descent to denoise a corrupted input at a specific noise level. The corruption process follows a cosine schedule, and we define the noise levels accordingly. We extend this definition for autoencoding by allowing the denoising function to take an additional argument, which accesses the uncorrupted input through the encoder. This results in a setup where the encoder, E, is learned alongside two decoders, a diffusion decoder and a secondary decoder. The secondary decoder helps us map back to the original image space, allowing us to concatenate the corrupted input with its pseudo-reconstruction. We also find that penalizing the secondary decoder speeds up training. Regarding architectural details, we employ a fully convolutional encoder in our experiments, inspired by MASC-GIT. This encoder consists of multiple stacked ResNet blocks, utilizing JLU for non-linearities and group norm for stability. We achieve downsampling through strided convolutions. The encoder architecture remains consistent across our experiments, with adjustments made only to the output layer to achieve the desired compression ratio. For the decoder, we use an architecture that mirrors the encoder. We implement depth-to-space operations for upsampling, maintaining the structure of ResNet blocks. For the refinement decoder, we utilize a U-net, which includes both downsampling and upsampling ResNet blocks, along with residual connections. After several downsampling stages, we incorporate a self-attention block to enhance the network's capacity. Section Summary. In this section, we discuss the limitations of traditional pixel-level loss functions like mean squared error, MSE, in image autoencoders, which often lead to blurry reconstructions. We propose a novel approach using a diffusion loss combined with a U-net decoder, termed Sample What You Can't Compress, SWYCC, which demonstrates improved reconstruction quality and lower distortion across various compression levels compared to state-of-the-art GAN-based autoencoders. Section: Speeding up training. In this section, we find that adding direct penalties to the initial discriminator leads to quicker training and better performance metrics, specifically CMMD and FID. We achieve this by minimizing a combined loss that includes terms with favorable properties and perceptual aspects. The function we use, called f_frozen, is a standard ResNet that has been trained on ImageNet and serves as a baseline for our work. We determine that the optimal settings for our total loss involve specific values for the hyperparameters, where one is set to 1 and the other to 0.1. Setting the second parameter greater than 0 is crucial for competing with GAN-based methods in our results. The visual benefits of using perceptual loss are evident in our figures. We believe that the main advantage of auxiliary losses is to accelerate training, as our diffusion decoder should eventually align with the true data distribution given enough data and time. For generating reconstructions, we apply classifier-free guidance during inference, and for our unconventional model, we train the U-net with some initial discriminator outputs randomly omitted in 10% of the training instances. In our experiments, we compare the GAN-based loss with our method. We define a relative compression ratio of 1 as a network that converts 8x8 RGB patches into an 8-dimensional latent vector. This means that for our encoder, if we have an input of a specific size, the output will be a smaller representation. To achieve a relative compression ratio of k, we adjust the size of the latent vector accordingly. Our results show that increasing the compression ratio leads to a more rapid decline in quality for the GAN-based autoencoder, while our approach maintains better performance across all levels of compression. The difference in image quality is clear, and we benefit from not needing to adjust any GAN-related hyperparameters, allowing us to leverage existing diffusion research effectively. We also note that the output from the initial discriminator is an intermediate tensor that isn't strictly necessary for the diffusion loss or final output generation. However, we demonstrate that this component is essential for achieving performance similar to the GAN-based autoencoder, particularly highlighting the significant role of the perceptual loss in reducing distortion. In our analysis of sampling, we illustrate how the number of sampling steps affects reconstructions. Even with just 2 steps, the overall structure of the image is recognizable. We further investigate how the number of sampling steps influences the CMMD metric and observe that only areas with high-frequency details are altered between samples, while larger, uniform color regions remain unchanged. We also examine the effect of classifier-free guidance in our refinement process, finding that a guidance scale of 0.5 yields the best results. This should not be confused with the guidance scale for the latent diffusion model, which is a separate parameter. Finally, we model the latent space using a DIT model for class-conditional image generation. We compare our latent representations with those from a GAN-based autoencoder and find that, despite using the same encoder architecture, our method improves FID by over 12%. We believe this improvement is due to our encoder not needing to capture high-frequency texture details, as our decoder can sample those independently. Section Summary. In this section, we demonstrate that additional penalization of the initial discriminator speeds up training and enhances performance metrics like CMMD and FID by employing a composite loss with favorable properties. Our approach outperforms GAN-based methods across various compression ratios, achieving better image reconstructions without the need for complex hyperparameter tuning. Section. Exploring better perceptual losses. In this section, we explore the effectiveness of different perceptual losses on reconstruction quality. We observed a significant impact from perceptual loss, which leads us to consider whether there are better auxiliary losses available. We compared the perceptual loss used in VQGAN with DISTS loss. DISTS loss has 2 key differences. It employs structural similarity index, SSIM, instead of mean squared error, and it utilizes features from multiple levels rather than just the last layer's activations. Our results indicate that at lower compression ratios, DISTS loss benefits GANs and SWYCC. However, at higher compression ratios, GAN-based autoencoders perform worse than those using perceptual loss. We believe this warrants further investigation. For our other experiments, we opted to use perceptual loss since it is more commonly referenced in literature and supports GAN-based autoencoders better at higher compression ratios. We trained all our models on the ImageNet dataset, resizing images to 256 by 256 pixels. During training, we cropped random sections of this size from images, while for validation, we used the largest possible center crop. Our models were trained with a batch size of 256 for about 1 million steps, roughly equivalent to 200 epochs. For our GAN baseline, we utilized a convolutional encoder-decoder architecture similar to that of MASC-GIT, which is widely used in image models and has been adapted for video by various models. We incorporated decoder enhancements from MAGVI-TV2 to improve reconstruction quality. Although video models enhance the architecture with 3D convolution for temporal information, we applied the discriminator and perceptual loss on a per-frame basis, keeping them unchanged in our model. In our SWYCC experiments, we maintained the architecture of the initial decoder identical to that of the GAN baseline. For the refining decoder, we employed a U-net architecture with specific modifications, including adjustments to channel multipliers, the number of residual blocks, downsampling factors, attention resolutions, and dropout rates. We used the Atom optimizer with a learning rate that warmed up over 10,000 steps and then decayed using a cosine schedule. We also implemented gradient clipping. For the latent diffusion model, we trained for 2 million steps with a batch size of 256, applying a classifier-free guidance scale and occasionally dropping the class embedding during training. All our experiments were conducted using a DIT-XL architecture.